All right, so we're going to cover section 7.3. And the title of the section is not a bunch of statistics. It lists 3 of the topics, but the truth is this section is just a bunch of statistics. So it kind of takes what we did in the previous 2 sections, and it does some interesting applications of those. So what we talked about was graphs of data or visualizations, right, of data. In particular, we talked about, let's see, I think it was histograms and bar charts, histograms. We talked about, sorry, that's supposed to be an H. Pie charts, stem and leaf plots, stem and leaf. Plots or graphs, I don't remember what our book calls it, and so forth. So we looked at visualizations of the data. Then we talked about like summarizing the data. We didn't really call it that, but that's what we were doing. We were summarizing the data. And we did that looking at the center of the data through the mean, median, and mode. And then we looked at how spread out the data was, and that was using the mean deviation and the standard deviation. And then here, I'm going to abbreviate that. Okay, so what we're going to do is we're going to kind of look at ways we can apply this information into statistics and give students an idea of where this can be used in the real world. So we kind of don't spend a lot of time on any topic. We just kind of hit a bunch of topics. So it's going to feel a little bit like moving kind of weirdly for that reason. But it's a lot more about broad understanding and not so much depth. Okay. Okay. So in order to talk about statistics, you have to talk about samples. So with statistics, the idea is to use a sample to represent a population. So statistics is about using a sample to represent a population. All right. And of course, that doesn't necessarily mean like the population of a country or a state or even a city. It could be like a school. It could be you're talking about adults, right? It doesn't have to be like a population in the traditional sense of a place that where you're living. It could be a group you're studying. All right. So the idea though behind this, if you're using a sample to represent a population, a few things need to happen. First of all, we need to make sure it represents the population. And the best way of doing that is to do what's called a random sample. So a random sample is a sample taken that uses chance. And what that means then is that every person in the population has a chance of being chosen to be part of the sample. So every person or thing, here, let's say member, maybe instead of the word person. So every member of the population has a chance to be chosen. So nobody's getting left out. That's how you know it's a random sample. And I wanted to use the word member instead of person, because even though the examples I gave a second ago were all people, it's possible that you're talking about like animals, pets, right? Like you could be talking about actual items, like you could be talking about cars and thinking about a sample of cars and how good their gas mileage is, or, you know, whatever the scenario is. So it doesn't have to be people. Okay, so it needs to be a random sample. Now, the ways of choosing random samples, there are a few different ways to do that. Old school way. So ways of obtaining. Now, most people, when you think about taking like a random sample, like the most simplistic version is like putting the names in the hat and, you know, swishing it around and everybody has a chance of being chosen. But if we're talking about something that's difficult, like, or very large, names in a hat aren't going to work. So the old school approach, and sometimes they still like to kind of do this, the old school approach. And that's where they use what's called like a random number sheet. So it's like this sheet of random numbers. A random, oh, sorry, I'm supposed to say number. A random number sheet. It's like this sheet of random numbers. And you could like literally Google it and you'll find like just this sheet of numbers. They have a sample of it in our book on page 462. But the idea is that if you randomly start on the random number sheet, and like how you choose to randomly start doesn't really matter. Somehow you're able to pick a random place, like close your eyes, point to it, and the number you're pointing on is your random starting point. The idea is you use that to generate a sample. I'm not going to go through that approach because, as it says, it's the old school approach. The approach that most people take is technology. And it's so easy. Literally, you could go and find a random number generator online. And it basically does the randomizing for you. So you can use an old school approach, and it's possible that you might end up teaching at a place that might want to talk about the old school approach, but really it's unnecessary. Most people are very comfortable with just doing a random number generator online. Okay, so you get a random sample, everybody has a chance of being chosen. Now, sometimes there are special types of samples you want to have, and in particular, the one they highlight here is the stratified sample. So a stratified sample is a sample that you take that includes specific categories. So a stratified sample divides the population into categories or groups. Into, let me actually say this first, non-overlapping groups. So you can't be in two groups. So like an example would be political party, like what political party you're affiliated to. You can't be in two, it's impossible. You'd literally be cheating the system. So you have to pick one and you're part of that political party. So stratified sample might be interested in looking at people's opinion by political party. So a stratified sample divides the population into non-overlapping groups and then takes a random sample of each group. Now, just to be clear, this type of sampling can be done, like even like with political opinions. You can do a stratified sample. Usually they do it like by some sort of phone tree where you get a phone call and they try to get your opinion via a phone call. Some people are really willing to take part in that, but of course, as you are probably aware, not everybody wants to take part of it. Some people don't bother answering the phone for something they don't know. You know, the list goes on and on. So getting these kinds of opinions can be a little bit difficult. But those are the challenges that statisticians face. Okay, so there we go. That's how like statisticians work. They try to get these random samples so that it's looking at the population, and then they basically pull information from the sample and say that that applies to the population. Okay, so that's kind of the big highlight for sampling, and they move right on along. So let's look at distributions of the data. Now we kind of have what we need for this, distributions of the data. So when we looked at histograms, let me just draw a couple of histograms. Actually here, I'm going to draw 3 histograms, and they're going to be very specific. Okay, so here, let's say the first one looks like this. Okay, And the second one looks like this. And the third one looks like this. Oops. I'm trying to make the rectangles as equal length as I can, but you know, I'm not doing all that great of a job. It's fine. It's just a loose drawing. Okay. So the idea is the first histogram that we see shows that the data is kind of clumped on the left side, right? It's the data is clumped to the smaller part of the distribution. In the middle one, it looks like the data is kind of clumped to the right side. And then the last one, the data looks like it's clumped in the middle. All right, so those have names. So let me go ahead and write those names. This first one is called skewed right. So that means that there is data that is causing the distribution to kind of pull out on the right side, have this kind of right side tail. All right. It's this idea that the data over on the right side here, on that side, that data is kind of skewing the data to the right, making the population look off-centered. All right. For some reason, it's unhappy that I'm trying to erase that highlighter. I don't know why. It's being weird. Let me see if the eraser button might help. Oh, nope, still not happy. So weird. Did I break my computer? Let's see. No, it's letting me erase that. It's just super unhappy. I was trying to erase the highlighter. All right, I'm going to redraw that. Technical difficulties. It's fine. Oops. Here. I think there was only 3, but whatever. Who cares? Okay, so skewed right. The middle one is then skewed left. We've got data on the left side that's causing it to look like it's kind of pulled off to the left. And then the one where it's all kind of centered in the middle, they call that a symmetric distribution because it kind of has like a symmetrical appearance. But we're actually going to give it another name in just a minute. So I'll go ahead and give it to you right now. It's also called the normal distribution. Now, that doesn't mean that it's normal to be put in the middle like that, because there's definitely examples of data that don't have normal distributions. What that means is it has some special properties, and often when you pick people randomly, it looks like this distribution. This symmetric distribution. It's also, by the way, called the bell-shaped curve. That's another phrase used to describe this data, the bell-shaped curve. I'm not going to write that down because I don't see that in the book, but it is also referred to as bell-shaped curve. Okay, said it 3 times, so there you go. Now, what it means, though, when the data skews right is that means what we have are potential data values that are higher than everybody else. So a good example for skewed right data is incomes, because most people are going to make lower, and then you might get a few people that make much higher than everybody else. So income is a naturally skewed right piece of data. A good example for skewed left is Alzheimer's disease. So people who get Alzheimer's tend to be older in age, but there are some people who get it younger. It's rare, but they do exist. So Alzheimer's tends to be skewed left. And then symmetric data would be something like IQs. That's like a classic example of symmetric data. Okay. So there's 3 examples of types of data. Now, here's what happens though. When you have pieces of data that are skewing, it also skews the summarizing things you use for the data, like the mean, median, and the mode. Okay. In particular, the mean. We talked about that, right? The mean gets messed up by outliers. And so when data is skewed right or left, the mean is affected by it. So here's what happens. When the data is skewed, sorry, I'm going to switch this to my red pen. When the data is skewed right, here's what we see on the histogram. So first and foremost, the tallest category, that is the mode. And then typically the median is in the middle. So it's usually right next to the mode. But then the mean is usually pulled out much further than it should be. And it depends, of course, on how far the data is pulling the mean. But that's what ends up happening. The mode ends up being the biggest category. The median is somewhere in the middle of the data, and then the mean gets pulled too far to the right. So it's much higher than the median and the mode. So with skewed left, it works the exact opposite. The mean is like over here somewhere. Here's the mode. And the median might be very close to the mode. Oops. Here, I'm going to abbreviate it MED just because of space. So there's the median in there. With symmetric data, the mean, median, and mode are all in the center. They're all in the center, very close to each other. So when we're looking at data that's symmetric or normal, we end up having the mean, median, and mode really close in value. All right, so let's go ahead and explore then the normal distributions. Let me switch back. So the normal distribution has some nifty applications. Now, often what they do is they take the histogram and they draw it as what they call a smooth curve. So instead of drawing it with the little rectangles like they do, they imagine, if you will, let me switch back to the red. They imagine, if you will, like this kind of smooth curve that kind of mimics what's going on with the data. So let me switch back to black. So in a normal distribution, then what we see is this is where the bell-shaped curve kind of comes in, this bell-shaped curve here of the data. Sorry, we can have this over there. And as I said a second ago, the mean, median, and the mode are all in the center of the curve. So the reason they draw it smooth is that actually gives it some interesting applications in calculus. Now, we're not going to get into those applications, but here's the cool things it does do for us. It gives us some really cool information about the way the curve works. So in the middle is the mean. And by the way, I don't think I've used this symbol before, but I'm going to. It is, the mean can be represented by X with a bar over it, or X bar. Often that represents an average. Okay. So in the middle is the mean, also the mean, the median, and the mode. Okay. All three of them are technically in the middle. So we're just going to call it the mean because we usually like to use the mean wherever we can, since the mean is a way of looking at every piece of data and including it. Okay. So here's what happens. We're going to look at the standard deviation. Now, the standard deviation also has a symbol we're going to use. And for some reason, they switched to the Greek letter for standard deviation. That is the Greek letter sigma. It is a lowercase sigma. It's a circle with a little tail at the top. There is a Greek letter for the mean that's used, just so you know, and don't write this down. It's called mu, and it looks like a U with a tail in the front, okay? They use the Greek letters usually when they're talking about a population, and then they typically use the American alphabet when they're talking about a sample. So because they've been talking about samples, they're using X bar because we've been talking about taking samples. And then they're talking about the concept that we're about to look at using sigma. It's annoying, and I'm sorry that they're doing that, but it is something you might see. Okay, so here's what happens. With the normal curve, there is some really cool properties that occur. The first one is that it does have this kind of symmetrical bell shape to it. And the idea is that data that kind of resides close to the mean has a higher probability of occurring. So data that is close to the mean has a higher probability of occurring. What it also means is that most of the data is close to the mean. In fact, if you go a little bit out from the mean, we are going to look at what percentage of the data is covered. So here's what I'm going to do. Give myself a nice big bell-shaped curve here to work from. And we're going to talk about the empirical rule. Okay, so the empirical rule is a way of kind of saying how much data is around the mean. So what we use to measure data around the mean is the standard deviation. So if I go one standard deviation above the mean, and here I'm going to use the abbreviation SD. Sorry, let me change that. Come on. There we go. One standard deviation above the mean, and then one standard deviation below the mean. So this is the standard deviations that we were calculating in the last section. Like that value, whatever it is, if it's like 5.5, right? You would add it to the mean and subtract it from the mean. And that ends up giving us a big portion of the data. In fact, it ends up giving us about 68% of the data. If you go one more standard deviation again on either side, one more standard deviation, that'll be 95% of the data. So 95% of the data is within 2 standard deviations of the mean. And if you go one more, as you can guess, we're going to get almost all of the data at this point. One more standard deviation. Here, I'm going to zoom out a little just to give myself some space here so we can see the big picture. That represents 99.7% of all of the data. All right. Are within 3 standard deviations of the mean. That is the empirical rule. All right. And there's like a really cool picture in the book of this where they've got like nice shading. I'll use my ghetto highlighter to kind of lightly shade this as best I can. So here in the middle is the 68%. And then here, let me change the color. So then we'll go to pink. Okay. And so the next group is 95%, those two. And then here, let me do one more color. What do you think? I don't know, maybe blue, a light blue. Oh, here, aquamarine, why not? Okay. And then the next one would be the 99.7%, 3 standard deviations away. Okay. Ghetto coloring. There's a much better picture in the book. And that's what the empirical rule tells us. So let me give this by an example. All right. Let me zoom back in just a smidge. Oh, too much. Okay. So let's say that the mean height for men is 70 inches, which is, by the way, 5 feet 10 inches. And the standard deviation is 3 inches. Okay. I don't know. I'm not writing out the word inches. There we go. Looks better. Okay. So using that information, if I'm saying that, you know, most men are 5 feet 10 inches, that's the mean. 3 standard deviations, 3 inches is the standard deviation. So let's talk about then what that means for the grouping of the heights of men. So what that means is that 68% of men are going to be, between 67 inches to 73 inches. So that's 68% are, and here I'm going to abbreviate between. Okay, sorry, I'm trying to do this in the 5 feet. So this would be 5 feet 7 inches. 5 feet 7. Sorry, let's do it with the little dashes. So between 5 feet 7 inches and 6 feet 1 inch. And that makes sense that 68%, the majority of men are between 5'7" and 6'1", 68%. Okay, then if we go another 3 inches out, that means another 60. So we're subtracting 3 inches. So 64 inches and then 76 inches. So now that's representing 95% of the population. That's supposed to be a 5. Are between, okay, so now we're saying 5'4" and 6'4". Well, that like makes sense that most men are between 5'4" and 6'4". Are there men that are outside of that? Yes, there are, of course. In fact, if we go another 3 inches, now we're talking about 99.7% of the population is between 61 inches and 79 inches. And that would be 5'1" and 6'7". Now we know that there are people who are outside of that, right? There are people who have conditions that cause them to be little people. We have people that are very, very tall, abnormally tall, that play basketball or don't play basketball, right? But the idea is that the majority of the population, the vast majority, fall between 5'1" and 6'7" for men. And that's what the empirical rule is telling us. It's giving us these kind of loose ideas of the percentage of the population that fall within these parameters. But what we notice is that the majority really do kind of hit it within 2 standard deviations of the mean. All right. And that actually means that they have this kind of phrase they use for rare event. All right. A rare event. They define it later, but I feel like it's a good place to define it. A rare event means something that is outside of or more than 2 standard deviations from the mean. Something more than 2 standard deviations away from the mean. Sorry, it's kind of getting fuzzy because I'm going low. So away from the mean. There we go. It's a little happier when I get away from the bottom of the screen. Okay. Cool. Now, the next thing they kind of spend a little bit of time talking about are percentiles. So this is something, especially in school, that we're pretty comfortable with. So really quick, I just want to define a percentile. So the percentile of a data set is a number that is greater than greater than that percent of the data, the given percent of the data. So let me give an example. Let's say I tell you that a student scored in the 90th percentile on a test. So a student scored in the 90th percentile. And here, how about I say on a national test? On a national test. And, usually they're standardized. So they have a normal distribution to them, by the way. Okay, here's what that means. That means that the student scored better than 90% of the other test takers. Or let's just say other test takers. I like that phrase. Kind of gives it a unique phrase for student. So that's what that percentile means. And then of course you could say that means that they scored less than 10% of the other test takers, right? So you can kind of do the opposite percent as well. But that's what a percentile is. It's talking about their score relative to everybody else. And it's thinking of it in terms of how it's greater than. So when you say somebody's height is in the 25th percentile, what we're saying is that they're pretty short. Well, they're only taller than 25% of people. That means they're shorter than 75% of people. The special percentile we should probably know is the 50th percentile. And the 50th percentile would be the median. It's the middle of the data. Okay, they do have two other percentiles they give special names to. That is the 25th percentile. They call that the first quartile. So thinking of it as splitting the data into quarters, the first quartile. And then the 75th percentile would actually be, oops, I just realized I skipped the I, would actually be the third quartile. So the second quartile is technically the median. Just so we're clear. So that one would be the second quartile, but we really only give special labels for the 25th and the 75th because the 50th percentile is more important as the median than it is as the second quartile. And they also like to give labels to it. So they call this one Q1 and this one Q3. And then of course, Q2 could be the median if you wanted to call it that, but most of the time we're calling it median. All right. Let's look at z-scores. So z-scores is a way of measuring a single data value's distance from the mean in standard deviation. So it measures a single data value's distance from the mean in terms of standard deviation. So it has a formula, but let me give an example really quick of what that means, okay? So let's say John has a z-score of 1 on SATs. Okay, so John took the SATs and he got a z-score of 1. That means he is 1 standard deviation above the mean. So they kind of switch back to talking about standard deviations after kind of talking about percentages. So it's 1 standard deviation above the mean. All right. And then let's say Bev also took the SATs and she got a z-score. Yeah, there we go. Oops. Too many dots. She got a z-score of 2. That means she's 2 standard deviations above the mean. I'm going to abbreviate this as SD, 2 standard deviations above mean. So I'm kind of doing bad English. So she would have scored better than John because she's even higher above the mean than John is. All right. So z-score gives us a way of kind of comparing data And what's kind of cool about it is it allows us to compare data then on unrelated matters. Okay, so before I give how that would work, an example, we're going to use John and Bev again, but I'm going to change the parameters. Let me give you the formula for z-score. And it's such a simple formula. It is z equals x minus x bar, so that's referring to the mean, over sigma, the standard deviation. And x is the data value that we're interested in, that we're trying to measure how far away it is from the mean. Okay, so here, I'm going to come back to my previous two people, but I'm going to change it a bit. This time I'm going to tell you that John took the the SATs. John scored 572 on the SATs. And Bev scored, oh, wow, it's not writing. Bev scored 28 on the ACTs. So she didn't even take the SAT. She took the different standardized test, the ACTs. Oops, that doesn't look like a C. Let me fix that. Sorry, I'm gonna cough. Okay, there we go. ACTs. So, and they still have their 2 z-scores, okay? The z-scores from the previous example. He got a 1, she got a 2. But what that really means is that on the exams, Bev did better in performance on the ACTs than John did on the SATs. That's what that means. So it allows us to still compare them, but without needing to look at it. Now, let's go ahead and let me show you the work associated to the actual means of the SATs and the ACTs, okay? So John scored 572, Bev scored 28. Okay, so now what if I told you that on the SATs, the average is 460, mean is 460, with a standard deviation of 112. So that's how the scores lay out on the SATs. And then for the ACTs, and by the way, they're not being specific about which version of the SATs, whether they talked about English or math. Oh no, they actually were specific. They talked about math, whatever, it doesn't matter. All right, for the ACTs, the mean is 18 with a standard deviation of 5. So that scoring system is a much lower scoring system compared to the SATs. Okay, so here's how we would, oops, sorry. I want to calculate the z-score, literally using that formula, okay, and this information. So let's start with John. So we're going to take the data value minus the mean over the standard deviation. So for John, his z-score is his score minus the mean for the SATs divided by the standard deviation for the SATs. And if you plug that into the calculator, it'll come out to 1. For Bev, her z-score would be calculating 28, her score, minus 18, the mean on the ACTs, divided by 5, the standard deviation, and that comes out to 2. So there you go. That's how you actually calculate those z-scores, and it allows you to just do comparisons between different types of examples, like without it needing to have to be related to each other. And that's it, guys. We did it. We talked about all the stats examples. Thanks for hanging in there.